Welcome to the office. Let's take a look at an example of classifying a quotient group based on the fundamental theorem of finitely generated abelian groups. Now, sometimes what's convenient for us to do is to actually go ahead and discuss the structure of a group based on the order of the group itself. So the order of the quotient group is going to be critical in determining the structure of the group. We'll find this approach is used a fair bit. So if I wanted to do that, what I want to remember is I want to find, so in general, when we're talking about G quotient by N, normal subgroup N, what we would do is we would find the order of G, find the order of N, and then remember that the order of G for a finite group here is the product of the order of N, that normal subgroup, and the index. So G, index of N and G here. So what we have is the index is the number of cosets of N. And that's exactly what our quotient group is it's the collection of cosets. So this identifies for us the order of the quotient group. So in this case, what I want to do is I want to recognize that the order of Z3 cross our direct product with Z6 is 3 times 6, which is 18. Easy enough. Then what I want to do is I want to recognize that the order of 0, 2 is what? Well, in this case, what I need to do is I can either go ahead and write out the elements that are in it, or I can use the order of these two individual pieces to determine the order of the element or the order of that subgroup. So if you're using the order of the two pieces, what you might do is you might notice that the order of 0 is 1 in Z3. Okay, 0 is in that first entry. So 0 is 0. We're good to go. That is the identity already. The order of 2 is, so we should be familiar with 2 times 3 is equal to 6, which is going to give us the 0. So this is order 3 in Z6. So the order of 0, 2 in Z3 cross Z6 is the least common multiple of 1 and 3. So of course, there's going to be more interesting examples than this, which has ordered 1 and order 3. In this case, it's just 3. So we know that. So then we can say that the order of Z3 direct product with Z6 is equal to the order of this subgroup 0, 2, what's generated by 0, 2, times the order of the quotient group that we're interested in, Z3 cross Z6, quotient by what's generated by 0, 2. And I know these two numbers here. I know this is 18. I know this is 3. And that's going to identify for us the order of the group of interest. Wonderful. Let's see. So that tells us that the order of Z3 cross Z6 quotient by what's generated by 0, 2 is equal to 6. Now that in and of itself is completely descriptive of the classification for this quotient group. Remember, the fundamental theorem of finitely generated abelian groups says that we can express every finitely generated abelian group as Z sub P P1 to the R1, direct product with Z sub P2 to the R2, direct product with all the way up to Z sub Pn Rn. Of course, if you have some copies of Z here as well, the Betty number, however many numbers there are there, a number of copies of Z, In this case, it's a finite group, so we know that it just has these things. But the point is that it is prime to a power. 6 is not prime, so the only way to split up 6 is as 2 times 3. So we know, according to the fundamental theorem of finitely generated abelian groups, that this quotient group can only be isomorphic to Z3 direct product with Z2, which of course is indeed Z6 if you're interested. Well, I guess it isn't exactly that. It's isomorphic to. So we can write it in this way. This is isomorphic to that according to the fundamental theorem of finitely generated abelian groups, but we can also recognize that that is also isomorphic to this. So that's what we're looking for. All right, we'll take a look at some more examples. What we've seen so far has been some pretty nice results of, hey, look, I can apply a theorem that I said previously, or I can go ahead and say that, use the order, and that's going to explicitly or immediately tell us what it's isomorphic to. So we're going to end up with some examples where that order does not immediately tell us, and that's what we have coming up here. So let's take a look at some more examples.